just waiting just a couple minutes here, a couple moments here. Waiting for folks to drop in. I just finished a shallot and now it's just gumming up in my teeth. All right, let's get this show on the road. Greetings, tech artists from around the world. It's Friday and it is 12:30 and it's time for Tech Art Talk Live. My name is Chris, and I'll be your host for today. Now, we've been on a visual effects rant for the last few weeks, and we're just going to continue moseying along on this visual effects rant. And today, we're going to be talking about, this is a big topic, gang. This is a really big topic. In my book on the real-time visual effects for the technical artist book, this should be coming out within the next few months. This is the biggest chapter. And so, therefore, I'm going to try to give you the Cliff Notes version and just condense this thing down as much as possible as we can and try to keep things going as cheaply and as ineffectually as we can, because otherwise it is going to be, I could talk about this topic literally for months. I dread the thought of this. In fact, large sections of the book have just been omitted just because we just don't have enough time. But with that said, let's get this show on the road and let's start talking about immaterial effects. Okay, now immaterial effects are the most common visual effects of all. And the reason why I call them that is because everything has to do with rendering. And it's all about rendering. Anything that you see on the screen is rendered. So therefore, it has to have some kind of material. If it doesn't have some kind of material, it doesn't get rendered. So therefore, if you have any kind of visual effect, it has to render in some form. So therefore, being able to manipulate how an object renders gives you enormous leverage in creating the world's most butt-busting visual effects. All right. Now, we're going to be talking about three different types of things today. We're going to be first talking about rendering in general, because we can't have too much of that. And then we're going to be going into what material and color operations. What can you actually do within a material? And then we're going to be going on and talking about texture mapping. And now texture mapping is probably the most significantly large component of this, because you could do these operations inside of the material and you could perform mathematical functions on it. But once you put context within texture mapping, then everything starts to skyrocket, literally. Okay. As a reminder, here are the 7 stages of the rendering pipeline. Now, everyone has to conform to this, and I call this, you master these 7 stages, then you master truly the art of visual effects, because then you're going to be able to manipulate the pipeline at any one of these places, and that's starting from left to right. Yeah. We got the input assembler. We got the vertex shader. We got tessellation. We got geometry shaders. We got the rasterizer. We got the fragment and the pixel shader, and then we have the final blending. So all those 7 contribute to be the rendering pipeline. Okay, if you're curious about more of that, check in the last Tech Art Talk Live. I believe that was episode 41, and we go all about the details on those. All right, now we got to talk about rendering. Now, how do you actually make something render? Well, these 7 stages are actually going into consideration. But what do you do with those 7 stages? What does this whole thing render? There are actually 2 big shading models. And the first one is the old school model. I call it the old school model because really it's the one that started off. It was invented years ago, like back in the 70s, over at the University of Utah by guys like Wei Fong, Ed Catmull, all these other guys that are luminaries inside of the visual effects world and the computer graphics world right now. Well, this is where they all got their start back at Utah, way back in the 70s. Anyway, they invented this, and they named it after the kind of like Phong. He's no longer with us, but they kind of named the basic shading model after him. And then we have the new school model, which kind of like started coming up around the 90s and early 2000s. And this is where you're going to get the Illumination Model. And the Illumination Model is also akin to what's known as PBR, or physically based rendering. All right, now I'm not going to go into too much about those. If you really want more about those, you'll have to go into prior episodes of Tech Art Talk Live. But let's start things starting with the good old Phong shader. Now, there's the formula for it. The old school renderer equals the color of the alpha plus the color of the diffuse times the K times the N dot L plus all of that gobbledygook right there. And that's the blue stuff is in the specular. Okay, believe you me, folks, this equation looks much worse than it actually is. It's actually pretty simple because all it really means is so your final color equals your ambient color plus your diffuse color plus your specular color. When you add those three up, you get your rendered image. You know, that's pretty easy, right? So let's take a look at what your ambient light is. Okay, take a look at this image. It might be real hard to see, but inside of that, well, you can see the shadow of my jack. And my jack is there. You can see it kind of like rough in there, and it's supposed to be dark, but it's not supposed to be black. Now that's the whole point, because this is what the ambient color is, what the color of your object looks like inside a shadow. And so it doesn't actually go pitch black, but it goes pretty much close to black. Okay, now the diffuse component is a little bit different because that's dependent on the light coming in on the object and the surface at which the angle at which the surface is pointed at. Okay, now this formula for this is some kind of constant times the light vector dotted with the n vector. You say, oh, dotting, uh-oh, that's some linear algebra stuff. That's beyond my, I'm not going to deal with that. No, but honestly, dotting is much easier than doing a cross product, believe you me. And that's what's going to give you the color of the light that is just reflecting off of the surface. Now, it's all based upon one big concept called the Lambert's cosine law. Now, if you take a look at that, it's all based on something called the law of cosines. And the law of cosines looks like this. Okay, don't freak out, gang. This is actually a pretty simple formula. So if you've got two vectors, you got vector A, you got vector B, and you're going to dot them, meaning you're going to multiply them against each other. Well, that ultimately equals the amplitude of A times the amplitude of B, or the length of A and the length of B, times the cosine of the angle, because you got two vectors, there's going to be like an angle in between them at any given time. Okay, that's going to give you that. Now, if A is unit length and B is unit length, in other words, 1, so therefore A dot B equals the cosine of the angle. You're going, okay, so what? Big deal. Well, actually, that's a huge deal, because really, take a look at this graph here. If you take a look at this little graph here, you can see the sunlight here is just pointed at the surface, and it's they got the surface normal pointing up. Now, because the light source is almost perpendicular to the normal, that means that the cosine is small. That means the cosine, because you know, cosine of 0 degrees, the cosine of 0 degrees is, is 1. So a cosine of 90 degrees is 0. And that's what's going on here. The angle between the light and the surface normal is 90 degrees, so that means it's pretty much close to 0. So that means you're not going to get much light. Now notice, as you bring up the light, or the light source, bring it up, and as you bring it up closer and closer towards the same direction as your surface normal, then the amount of light coming off is going to come up much, much closer, and it goes in a nice linear progression. And this is what's called the law of cosines, or the Lambert's cosine law. Now this is what gives you that nice smooth gradation that as the light kind of like wraps around the object, as it kind of gets darker as it goes into behind the object. Now that is what's going to give it to you. And now that is a super, super powerful formula, and it's even present in today's PBR, but we're not going to talk about that for now. Okay, and so what that does is all we're going to do is going to take the light vector and we're going to dot against the n vector, the normal vector, and therefore we're going to get our diffuse color that way. Okay, now things get a little little bit more popular with the specular lighting, but it's really not so bad. The specular lighting is going to give you that mirror-like reflection, because when you've got light bouncing off a surface, now how much light that is reflected off the surface and going right into the camera or right into your eye, that's what's going to create that specular hotspot. And so that's what kind of gives that mirror-like appearance. Now, what do you do with that? Okay, so this is what's called Phong Specular. Now this is an approximation of the reflected light directing bounce, directly into the camera. Actually, it's a lot more complicated than that, and that's what's kind of where we have the Illumination Model, because the Illumination Model pretty much replaces Phong Specular, but it took 20 years to kind of like overcome this little simple formula. Okay, now take a look at this little diagram. We have the surface normal in blue coming off here, and then we have the normal of the light in yellow. Now, when the light bounces off of the surface, it creates a reflection, and that's the vector in gray, and that's the reflection vector. Now, we're going to use the Lambert's cosine law again to kind of calculate the angle between the reflection vector and the camera. Basically meaning the more reflection that is bouncing right into the camera, the more you're going to get, the more light you're going to get. And that ultimately is the explanation of Phong Specular. It's really the reflection vector times, dotted with V. And that's going to get, and you're going to raise it to the specular power. And when you raise it, it kind of like makes the distribution of that specular component a little bit. As you get larger, the reflection, or the mirror-like reflection, gets smaller and smaller. If you get a smaller exponent, then it actually gets larger. All right, now what's wacky about this formula is that it's all about the reflection vector. As a reflection vector is dotting with the V, and then you take it to the S power. That's really not so bad. But what do you do in order to get the reflection vector? Well, that's a little bit of a nutty formula, and that's 2 times the n dot the L times n minus L. Okay, now I have explained this, I think, in a TechArt Talk Live. If you really want more about this, but this is the reflection vector. The reflection equation is all about visual effects, and it's all over the place. So if you haven't seen this before, get used to it, because you're going to see it again. But real simple, specular reflection is just the reflection vector dotted with the view vector and then taken to the S power. Okay, not too bad. As a reminder, when you combine the ambient with the diffuse and the specular, then you get the fully rendered image. Okay. That's Phong shading, or the old school model. Now the new school model is actually trying to duplicate how light actually does reflect off of the surface, because it's really kind of complicated, and it involves a lot of real physics, and it involves heat transfer and so forth. And so we've got physically based illumination, we got PBR, and oh yeah, here it is. Here's the reminder of there. Okay, if you really want a robust explanation of what the Illumination Model and PBR, check out my lectures number 24 and 25. Okay, so what is this Illumination Model? Okay, it's based on the law of conservation of energy, meaning like, okay, light is energy, right? Light coming into the surface, and then light bounces off the surface. Now that means that energy is neither lost nor gained, so therefore the energy coming off of the surface should equal the energy coming into the surface. Now that is basically the Illumination Model. That's what it all kind of like calculates. If you look at this model here, you see that here's the surface, and then we have the camera bouncing off in here, but we have this this omega. Now this omega has light coming in from all over the place. So it goes off in this one specific direction, and it goes off into this W vector. So all the light coming into the object equals the light coming at the camera and the light going in this omega direction. And that's where we get this lovely little formula. And so the output light equals the incoming light plus the the emitted light, which the light is actually kind of bouncing directly off, and then the light of the reflection. And so this is the exact same reflection, and it works into all of this formula. Now this formula is nasty. I'm just going to come right out and say it is. It's a whopper. It takes a lot of physics, and people are still getting their PhDs on it, I think. And so you're going, okay, if this is the real way of rendering, how are we possibly going to create materials in order to deal with this? It's too complicated. Well, what the modern real-time rendering engine folks have done is they've exposed a certain amount of controls to you, and it kind of like they're going to do all the heavy lifting and then just expose just a few parameters to you in order to give you control over this huge Lake equation. So they're going to give you controls to manipulate the vertex shader. You're not actually going to go and manipulate the vertex shader. No, 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 no. They're going to do that for you. But here are a few parameters to manipulate the vertex shader. You can manipulate the tessellation, or how the image gets chopped up into little basic pieces. You can do the geometry shaders. You can add a little bit of geometry, or you can subtract the geometry. You can go inside the fragment and the pixel shaders. And you can finally modify the final blending. Okay, so let's take a look at what these are all doing. So you've got the vertex shader. Now the vertex shader is really the only essential component in the entire rendering pipeline, remember. And so what you can do is you can manipulate the vertex normal. And when you manipulate the vertex normal, you're kind of like fudging with the way that it renders and make it seem like it's got more information than it really exists. Or you can manipulate the vertex position, and where you actually move the vertices around depending on some kind of formula. And there you get this wild, chaotic, wacky-do mess over there. But anyway, you can manipulate only two things, the vertex normal and the vertex position. Those are the only two parameters you've got to play with. Okay, what about tessellation? Now tessellation allows you to break up an existing object into smaller object, so that when you actually do the deformation on it and you do the manipulation of the vertexes, it actually looks like it looks pretty good, and it maintains its shape and it doesn't look all jaggedy. All right, now the geometry shader, this one still hasn't really caught on yet. As a reminder, it allows you to remove or to add vertices and polys. But honestly, folks, it's still kind of awkward to manipulate. And if you're going to do any kind of manipulation of the geometry shader, you're going to have to bust open into the engine and start playing with the engine itself. Now, I know that the programmers don't like you doing that. That's why they're exposing all these controls to you. But if you want the power of the geometry shaders, you're going to have to put on the old diving mask, swim fins and snorkel, and dive in there, folks, because you're going to need to hold your breath for a while. Okay, now the pixel and the fragment shaders, now this is where most folks come in, and this is where the Illumination Model takes in. This is where your standard PBR parameters come in, where you're going to manipulate your base color, your metallic, your specular, and your roughness, and your normal. And okay, you're going to get the ambient occlusion. So this is actually kind of complicated here, a lot of stuff to deal with, but if you go back to my lecture on PBR, which is, I believe, number 25, I think. But anyway, I'll show you how. Go ahead and manipulate each one of these parameters. Oh yeah, we're going to have to deal with the opacity as well. Okay, now here's the last one we got to deal with. Now we haven't really talked too much about this. This is about blending. Now every time the rendering engine layers one object, that's one particular layer. But what if you have multiple objects, and then how do they blend on top of each other? Well, the engine has to blend all these things together, so therefore there are a couple of blending parameters that you have to deal with. And what you got to deal with is like the opacity of the object and the emissiveness of the object. Now these are all manipulated inside of the blending. Now the thing to remember about blending is that there are certain blending modes, and the blending mode function is, it's not too complicated, but it takes a little bit of getting used to. So therefore the rendering folks, when they were creating the rendering engine, created a bunch of kind of like modes for you to kind of like do all the stuff for you. Instead of you having to deal with all of the other possible permutations, they kind of make it simple on you. You're going to deal with opaque blending, mask blending, A over B blending, linear dodging, and linear burning. Now if this might sound like standard mathematics of colors, well, guess what, folks? That's what it is. It's just mathematics of colors, exactly. So let's go into explaining these a little bit more in detail. Okay, first we have the opaque mode. Now, actually, I have the demonstration here for you. All right, this is opaque mode. See, we have got this cube here in front of this sphere. Now, the sphere has a very fancy visual effects material on it, and actually so does the cube. But look at the cube. The cube is in front of the object, but you can't see anything of the sphere when you're looking at the cube. The cube is right there, so it's moving right on there, but you can't see any part of the sphere. That's because this cube is rendered as opaque, meaning you can't see anything through it. So therefore, no matter what happens, you don't see anything through the opaque cube. Okay, so the next one is the mask. Boom, boom, boom. Okay, now the mask, if there is any kind of color, then that color is opaque. If there is no color, then that portion is transparent. So it's really simple. This is actually called alpha testing, because really we don't really have an alpha channel here. All we have is color. So if the color exists, then the transparency is 1, meaning it is opaque. If there is no color, or otherwise it's black, then it's fully transparent. It's either transparent or it's opaque, one or the other. That's simple alpha testing, or that's also called masking. Okay, now we have the standard like A over B model. Well, this is what most people are used to. I'm going to have to get in a little bit close to this. Okay, you can actually now see a little bit of the sphere in front of the cube. Now you can see there's parts. It's no longer opaque. What I have here is an actual gradation, and so it's gradiating. You know, I have a little bit of a mask on here that kind of fades from left to right. So left is totally transparent and white is opaque. And so as you can see, it kind of gets less and less transparent, but you can still see the sphere behind it. Now that's your standard A over B blending. Now when you're talking about blending, most people think about this type of blending, and this is what goes on in most people's head. But actually this is not everything, so this is a big portion, but it's not the whole shebang. I would say 80% of most of your blending has to do with this. Okay, this is also called alpha blending, by the way. Okay, now we have linear dodging. Linear dodging is another word for addition. Now notice here that the black's still here, nothing's coming through. That's because the alpha does. But whenever you see whenever we see the color of this cube, it adds with the color of the sphere. Now those colors are added together, and so what this is going to have an effect of is this has to brighten the object. Wherever the two layers are intersecting each other or overlapping each other, this has to overlap. Oops. They have to add, and they have to get brighter. Okay, we've got things set up here. All right, now the next one is linear burning. Now linear burning is kind of the opposite. So here we have the color of this thing, and it's going to multiply against the background. Now here remember that the color in this is black, and so therefore when we render black against the sphere, then that means you can't see it. But here we have is a little bit of color. We've got this magenta, and so when we multiply the magenta against the color of the sphere, then the object gets a little bit brighter. So linear burning, well, I'm sorry, it gets a little bit darker. I'm sorry. If you look here, the sphere is a certain intensity. Whenever you see it through the cube is multiplying against the sphere, and it's making it dark. So it's always going to make it a little bit darker. Okay, now let's talk about the basic material operations that you're going to deal with. Okay, so we have the multiplication. When you multiply two colors, what happens? They're going to get darker with each other. what happens when you have addition to together? Then they're going to get brighter no matter what. Now there is a third operation that you're usually going to see, and that is called lerping, or in other words, linear interpolating. Now this is actually a very common, and it's a good way if you want to go between one color and another color. You can go part way from one color to another. And it's very, very handy. So when you multiply colors against each other, you're going to end up with objects that is, inside of each other. Now, when you here in this image, I have two layers of colors multiplying against each other, and what this actually has a tendency of doing, if you'll notice, it makes one object appear to be inside of another object. If we were to look at this, cube once again, notice that this cube, if we were just rendering the cube and multiplying against the sphere, and we just wanted to see the cube, you would see that the sphere looks like it's inside of the cube. Now that's the whole point of multiplication. Multiplication, the overall effect is that making one color be inside of another color. Now I know that's a little bit abstract. That's why we have all these examples here for you. Now when you add two colors together, it's going to brighten or darken with the color depending on what you add here. Now I have a simple thing example here where I've got my jack. I'm going to add against gray here, and so it's going to add a little bit brighter. It's actually not going to get darker. In fact, it's almost like you can't get any darker when you add. So it's always going to get brighter. So if you were going to add black, then when you add black to a object's base color, it's going to stay basically the same. Okay, now we're going to go talk about lerping. Lerping is, it has to be seen to believe. Okay, what we have here is that I'm lerping between two colors. I'm lerping between green and I'm lerping between magenta. And so it's ping-ponging back and forth between green and magenta. From green to magenta, but magenta to green, back and forth. Actually, there's a sine function driving this behavior on here. But anyway, you see how nice and smooth this transition of color is, and that's because the two colors are linear interpolating with each other, and this is an example of lerping. Okay, so let's talk about texture mapping. Now, texture mapping is probably the most powerful component inside of the immaterial being, because texture maps allow you to use whole bunches of colors and stack them up against each other. And now, what is texture mapping? Texture mapping is wrapping a bitmap around an object, and it uses the UV coordinates of the object in order to index of where the bitmap maps onto the object. And so if you look at this little diagram, we have this plane of this object, and it's being projected right onto this flat surface, and so therefore this object is the texture map for this planar object here. And that's ultimately what it is. If you can think of texture mapping as shrink wrapping a picture around an object, and that's why you have texture mapping. Okay, now you can have more than one set of texture coordinates. Remember, I was talking about the UV coordinates that help map the texture image to your object. Well, you can have multiple sets of texture coordinates, so therefore you can have multiple maps on one particular object. Now, if you see in this example of this cylinder, the cylinder on the sides is wrapped with one set of UV coordinates, but the top of it is wrapped with another set of UV coordinates. So we've got two entirely different textures on this object at any given time. So it doesn't have to be limited to just one. You can, and actually, when you're dealing with multiple texture coordinates, now you're really starting to deal with power and opportunity. Now, what kind of operations can you perform on the textures? You could do scaling. You can do offsetting. Okay, so let's talk about texture scaling. Oops. I'm going to have to go back onto this lecture now. All right, so let's talk about texture scaling. Here we have, what we're doing is multiplying the texture coordinates inside of my cube. And all I'm doing is just taking whatever the texture coordinates and I'm multiplying it between 1 and 4. When it's 4, it gets real bitty. So that means like you can see 4 duplicates of the texture map inside of it. When it goes back to 0, it gets really big. It gets huge. In fact, it doesn't go away. And so scaling is one of the first things you could do when you're dealing with texture coordinates. Scaling is very, very powerful. Okay, now when you're scaling, you can also offset texture coordinates. Now here, I've just offset, I've done a scale and an offset, honestly. I scaled it down, instead of multiplying it by 2, I multiplied it by 0.5. So I got just a quarter of that texture image that I had on there. And then I offset it by 50%. And so now I'm looking at just the skull guy looking at us here. And so offsetting is a really, really powerful way of manipulating the texture coordinates. Okay, here is, we're going to deal with animation. So how do you animate textures? Textures are animatable, and that's one of the cool things that makes them so powerful. You have a various number of functions, and there are 4 functions. You could do flipbooking, you could do panning, and you could do rotating, and you could do procedural animation. Okay? Now let's look at flipbooking here. What we have here is a flipbook. This is one texture, and it has 64 frames on it. You'll notice that it has 8 versions of Roberto, 1, 2, 3, 4, 5, 6, 7, 8, and 8 rows of them, 1, 2, 3, 4, 5, 6, 7, 8. Now, what we're going to be doing with this flipbook is this showing one texture and then showing one texture another, and we're both using scaling and offsetting at the exact same time, and we're doing this, they're playing them in sequence. And what this has to do, and that this actually makes Roberto look like, now this is really cheap. This is just one, I don't know if I click on this, okay, it's not showing up here, but really it looks like it's a 3-dimensional object, because what I did was I rendered Roberto breaking up into pieces in a separate process, and then I mapped them all into here. But you can see that this is just a plane. You can see a little bit of clipping going on here, and so this is just a single plane. So this Roberto looks like he's on there and he's breaking apart. You'll say, man, this is going to be a real expensive visual effect. No, it's super cheap, because all we're doing is we're rendering a plane with one texture. So this is what it is, gang. That's all it is. It's really, really cheap. Okay, panning. Oh, gang. This is where things really start to get cool. Okay, so what we're going to be doing here is instead of scaling the textures, we're going to be panning one, or otherwise we're going to be translating them. And here in this situation, I'm translating both in the U and the V direction. And you'll notice that this kind of looks like it's almost a 3-dimensional effect, because that's the intention it's supposed to happen. But really, this looks like a real complicated effect. But no, this is not a raging fire. This is really just a texture map of a fire, and we're just kind of moving it just very subtly in the U and the V direction, and this is where you're going to get most of your panning. This is a really popular tool, gang. If you ever play like something like League of Legends is like composed of almost all of panning textures. I mean, it's uncanny, but this is we could go on and I could give you hours and hours and hours of examples and demonstrations on how to manipulate panning. Okay, the complement to panning is rotating, or in other words, we have a rotator. Okay, guess what, gang? All these text floating around in midair, floating around, rotating. Guess what? This is just a still plane. The plane isn't rotating. It's staying in place. You can't see it because the texture coordinates are being rotated. Now, I don't have time to go into the explanation of how to rotate texture coordinates, but it's super duper simple. So all I'm doing is I'm putting this texture map onto this object, and I'm rotating the texture coordinates. And this has the effect of making it look right. Now, if you're really going to get tricky, what you would do is you would get the red layer, the green layer, and the blue layer, and then you would animate each of those layers independently. but that would all be in one shader. That would be in one material. So you're going to get all this complicated motion just with one material. Super duper powerful stuff, gang. Really, really powerful stuff. Okay, now the last one we wanted to do is talk about procedural. Let's see, do I have a slide for this? Yeah, I do. Okay, that's when you use a mathematical function to offset the texture coordinates. Or you could offset the color. It doesn't really matter. You're using some kind of function on here. Now, if you remember, when I was lerping, let me see if I can go back and show the lerping. No. Oh yeah, there it is. Okay, I'm using a sine function to lerp in between green and blue. So a sine function is one of these procedural functions you can do to manipulate the object's color. Now, what I'm going to focus on primarily are functions in order to manipulate the vertices of an object. When you say manipulating the vertices, yes, you can create actual real animation. Now, this is not real animation, gang. The object here is staying static. It doesn't change position at all. But what if you wanted to use these texture maps and so forth and procedural functions in order to manipulate the actual vertices on this? Yes, you can do that too. And so this is like when you're working with procedural animation, you got the sine wave, and then you got these things called random noise and fractals. Okay. Random noise and fractals is a big topic. Now, I could just give a lecture topic just on randomness, just on noise, and just on fractals. It's that huge. In fact, it's almost like an entire course all of itself. But you have to go and say, like, okay, that's something for else to learn on. But let's start talking about using these functions in order to manipulate these vertices. Okay, here we go. Okay, this is one of the most popular ones. Here we go. This is a pulse. So all I'm doing is I've got this texture map, and then all I'm doing is using this texture map, and then I'm running this texture map using a panner up this entire cylinder. Now, instead of manipulating the color, which of course I do anyway, but what I'm doing is I'm manipulating the vertices, and I'm basically moving the vertices or displacing the vertices outward along the surface normal based on the presence of this texture map. And so we actually see this comes across looking like a pulse. And this actually pulse is kind of like creating the effect. This could also be used for creating a waving flag. Yes, this looks like the flag is waving in the wind. You're saying, oh man, that's going to be expensive. I'm going to have to go and do a brilliantly huge simulation on this in order to get this on. No, you don't, folks. This is really simple. This is really quick and easy. All I've got is a sine function going through this. You say, this is just a sine function? Yes, this is just a single sine function running through this, and it's making this manipulate and flap around in the wind. And this is all this is, and this is super cheap. This is really inexpensive. This can also be done for using liquid effects. Now here, I'm not necessarily very proud of this, but this is some stylized water. Now you're going, okay, this is a stylized water. Well, it is stylized water, but all I'm manipulating here are the vertices. You can see this was just a plane, but you can see I've got a sine wave going through this, and actually I've got 3 different sine waves and a water drop going on in here, and they're all adding and complementing each other. And so what you see here are the normals of the surface kind of making things look a little bit chaotic. There is no color manipulation going on here. Basically, folks, all I have here is blue, and the rest of this is all handled in the Vertex shader. You know, pretty amazing stuff. And this is like you're playing, oh, this has got to be really expensive. Whenever you're dealing with water materials, it gets really expensive. No, it's really cheap. It's because this is just a plane here, and we're just manipulating the more normals you thought. Now, if I really wanted to make a much better water, then what I would use is something called like a Gerstner function. Now, a Gerstner function is a little bit more complicated, like, oh, what's the fellow's name? There's a guy out there on the web. He shows how to manipulate just manipulation and material manipulations inside UV4 editor. Really, really good guy. I'll remember it just in a little bit. It's coming here, but he shows all about how to set up for Gerstner waves, and it's a little bit complicated, but I can't steal his thunder. I said, like, check his information out. And this could also be used to scale your character. Okay, there I got is good old Zangief here. And what I'm doing here is I'm just using a sine wave to, once again, I'm scaling the character up and down, up and down. Okay, this character looks like he's doing some complicated business. But no, this is all happening inside of the shader. And all the vertex, all the animation is going on inside of the vertex shader. In fact, if you see any kind of articulated motion, then that articulated motion is happening inside the vertex shader. When you see an arm bending, it's happening in the vertex shader. If you have a character running around, shooting a rifle, it doesn't matter. It's happening inside of the vertex shader. So it's all happening in there, and and this is the reason why it's all real cheap, because it's happening right within the vertex shader. Okay, very, very inexpensive, folks. Okay, thank you very much for hanging with me and sticking with me, because I know I've gone through a lot of stuff on here. Uh-oh, what did I show here? There's my flag. There's my pulse. Did I have my wrong things showing on the whole time? I hope I didn't. But anyway, here's the pulse. In case I didn't show it, here's my flag. There's my water shader. Oh, I'm showing the wrong thing again. My bad, folks. Okay, let's go on and wrap this up. I can tell I have worked way too hard on this, and for far too many eyes to view. Okay, this is what I wanted to focus, and this is like good stuff here. Now, if you want to come out and continue on this exploration into the world of visual effects, tune in next week for Tech Art Talk Live, where I will show in the wonderful world of simulations. This is happening on May 14th. We're going all about simulations. Simulations is almost as big as in material visual effects, but it's kind of like different. And we'll go into the pros and cons of simulations next week. Now, not as many demos on here because simulations actually are real expensive as opposed to in material, but we'll get on to that next week. Okay, if you like what you saw, go ahead and subscribe to my channel. Go ahead and check me out, subscribe on YouTube, or check me out, Chris Rota, on Facebook and on LinkedIn. And check out Tech Art EDU, also on Facebook and on LinkedIn. Okay, but if you really want to help me, go check out the techartedu.com and go ahead and opt in to my newsletter. When I do start, I know I've been promising newsletters like forever. They'll happen again someday, gang, I promise. But when you opt in, I'll be sending you newsletters and give you information of everything that's going on here in Tech Art EDU. Well, thank you very much for putting up with all of my shenanigans and all of my technical foibles. This is what I get when I'm a one-man army. Yeehaw! Anyway, I look forward to meeting with you again next week when we go into simulation effects. And until then, I'll see you then. Bye.